Hi, I'm Andrew Lin. I'm a CSE major at UC Merced, and I worked on defect detection at Advantest. A big problem in producing any type of good is to sort out the defective products from the working ones. As a semiconductor company, you'll be asked to look at lots of components, so it's best to find a way to automate this process. It's painful to sort all of these parts out manually, and any mistake is very expensive. I was tasked with creating a vision system that would identify defects in industrial parts like nuts, bolts, screws, sometimes even toothbrushes and bottle caps. Although not computer chips, the process for sorting out these items is similar. Images of these items are all part of the public MVTEC AD dataset. My advisor started me off by suggesting to use machine learning. I immediately tried deep learning, which involved getting a convolutional neural network to train on the dataset. I ran into one problem though. There wasn't enough training data. Then I tried a more traditional approach, which was to use a decision tree. Decision trees usually take a dozen to a few hundred features, so it felt weird at first because I was giving an input of hundreds of thousands of features, each feature corresponding to a pixel on the image. But it worked out pretty well, giving an accuracy of 80%. Additionally, I learned how to use Python libraries like PyTorch, TensorFlow, Keras, and I was able to navigate through the Amazon Web Service interface to create an instance that runs my code. To pre-process the dataset, I used a library called scikit-learn. I was given a loose goal to work towards at the beginning of the project. Do I need to segment images into defective and good regions, or did I just need to classify whether the whole image was good or bad? I first started with image segmentation because there were already state-of-the-art models available for image classification and I wanted to try something new. But I later decided to go down the classification route. Looking back, it all turned out okay in the end because I was able to borrow code that I wrote from the segmentation process. Before switching tasks, I came up with a way to segment the image. I first pass tiny windows over all the images and find which windows are worth considering. Then I apply a gift wrapping algorithm to outline the defective area. Finally, I apply a clustering algorithm to group regions together. It was very exciting to put what I learned from textbooks into actual practice. The rightmost column is an example of the process. It's far from perfect, and someone in the future will be able to improve on the process. I'm grateful that my host company provided me with AWS access. My mentors were always available whenever I had questions to ask, so thank you Vijay and Nidhi for guiding me through this project. And thank you for listening.
Hello everyone, my name is ZhiBin Huang. So the campus I went to is the University of California, Santa Cruz. And this summer I internship in the UCSC lab called Vertical Architecture Memory and Algorithm. And for this summer, the code I'm using is called the GAP benchmark, and then it is a C++ code programming language. And as you can see on the picture below, I use the BFS, SSSP, PR, CC, BC, and TC. Those are the code for the graph research by evaluation and calculate the speed. And they all put on the file right here called benchmark, and there are many interesting code inside. And for week 1 to week 4, I learned the basics learning and work around how the gap codes run. If you can see the picture on the left-hand side, this is the code from the professor. And then if you can see the code on the right-hand side, this is the code from the git request from other people. So on week 5 to week 6, we go on more deeply running testing. If you can see the picture on the left-hand side, you can see that I doing some research by using the website called stanford.edu. And the left-hand side was the original code from professor. I run BFS, BC, and CC. On the right-hand side, I use the pull request. I also run BFS, BC, and CC. And I compare the speed for both of them. I find out that the pull request is kind of a little bit faster than the professor code. We're also doing an interesting challenge called 100 times challenge. On the first picture, I run a for loop to set the counter equal to 0 and the number of time I want to run. And the picture below, you can see that the first one, BFS, is the function I want to run. And the second one was the graph. And lastly, the last one was the times I want to run. And And lastly, I run the ALS. I learned ALS, but I didn't really find out that the main idea of ALS is an algorithm to discover the volume, such as the non-zero entry in R can be by the dot product and row and column vector, or you can understand as the matrix factorization of ALS. So for the future, I am still interested in being a computer programmer because there are many job opportunity, and choosing this area can be open the door for many job opportunity. Some of the many job in this area are machine learning or C++ developer. Thank you for watching.
Hi everyone, my name is Claire Gantan and I am a senior at UC Berkeley studying electrical engineering and computer science. This summer, I had the opportunity to work at Advantest on designing automated test equipment. During my internship at Advantest this summer, I was tasked with the goal of developing an electronics board for testing purposes. Advantest is a leading company for creating automatic test equipment, or ATEs, for the semiconductor industry, like the one that's pictured here. I was working on creating a custom electronics board based off of specific electronic components. ATEs in general are advantageous within the semiconductor field because you are able to accurately and quickly test if a device is working the way it should without the time or error of human testing. As I mentioned before, I worked on developing an electronics board, which involved designing a digital circuits interconnect schematic shown here. This schematic is the diagram of all components on the board and how they interact with each other. One challenging aspect of my project was identifying optimal power components for the system and designing the onboard power supplies. This involved calculating board power consumption as well as thermal characteristics. Another challenge I worked on was the clock components, specifically looking at the source clock and clock distribution within the system. Through this work, I learned how to determine the correct interconnect between components, while still keeping optimal signal integrity. I was able to truly appreciate the thought and expertise that goes into developing custom circuitry throughout this part of the project. I also implemented Verilog programming for the FPGA-based digital interface with timing and interconnect constraints to control the onboard devices. The FPGA device was used to compare the expected values of the device with the actual data signals coming out of the device. The electronics board that I was able to develop was quite generic, so in the future, some next steps could be to customize the board to a specific chip or customer. And I was also able to sit in and learn from meetings of other colleagues who are working on different boards. And from that experience, I learned that different countries have different regulations for tech imports. Therefore, another step to advance this project could be to determine the constraints of the customer's market and further refactor the board design. I'm truly grateful for the experience that I was able to have at Advantest, and I learned so much about what it means to be an electrical engineer within the semiconductor field. I also wanted to give my thanks to my managers and mentors at Advantest, Peter Balloon and Roger Michelinen, for guiding me throughout this summer, as well as to Vivek, Nicole, and Faye, as well as all the other students who are part of the CITRIS Workforce Innovation Program. Thank you.
Hi everyone, my name is Yeiji Lee. I'm a junior studying mechanical engineering at UC Berkeley. My pronouns are she, her, hers, and today I'll be talking about my work on the CITRIS Workforce Innovation Program. So over the summer, I was paired up with a company called Advantest, and I was put on the device interface team as a mechanical engineering intern. And the main project that I worked on during the summer was the duct mini chamber project. So the main problem this was supposed to address was that there was currently too much noise when cooling down the loopback cards or any type of cards that the clients would want to test on. So the main motivation on using a chamber was basically the chamber would cancel out any noise that the fans or the cards would make. And pushing cold air through the chamber would also cool down the loopback cards or any cards that they wanted to test by cooling them down essentially and making sure they don't get too hot. And I entered this project during the prototyping stage, so a lot of my contribution went into design, simulation, and testing. So some technical contribution and learnings that I did in June was that I experimented with the prototype and ran a lot of tests on them. The main challenges that I ran into were calibrating the testing system with the prototype, basically running different types of tests at different temperatures of air consistently. And in July, I did a lot of calculations and design changes for this project, including on learning FMEA, which is failure modes and error analysis. As you can see on the top right, it is an example of one of the calculations that I would do with thermodynamics, as I have also learned thermodynamics, heat transfer, and statics as a review with this project. And in August and onwards, I guess I did a lot of heat and flow simulation work on SolidWorks. And this was done using online resources, getting advice from our main engineers, and basically learning how to work all these different types of simulations. So I'll be continuing this internship till the end of winter, and this is because this project was designed to end or get into production by winter. So, and the next steps would be doing a design review on the mini chamber, optimizing the simulation, finalizing codes on parts, and building a prototype, and as I said before, get into production by winter. And before I end this presentation, I just wanted to say a big thank you to Kapil IOR, who is the manager for the DI team, Gerald Chu, who is the main engineer behind the mini chamber project, and the rest of the DI team for an amazing summer. Thank you so much.
Hello, my name is Joseph Barrera. Today I'll be presenting on simulations for stable low-temperature plasmas. I am a third year at UC Merced studying computer science and engineering, and this research was done under the Ayyaswamy Lab at UC Merced. So what is a low-temperature plasma? A low-temperature plasma is a plasma, as the name suggests, is lower temperature when compared to similar plasmas found in nuclear reactors. This type of plasma is used mainly in water purification, synthesis of nanoparticles, and chemical conversions. What stuck out to me was that it is used also in semiconductor design, especially for 3D transistors called FinFETs. These types of plasma, although very important, do not have specified software that is able to model them, such as their cousins in nuclear reactors. Thus, the Ayyaswamy Lab is mainly tasked with trying to create a software that is able to accurately model them, while also creating a variety of parameters that they can be modeled within. This software uses PIC, which is particle in cell modeling, which uses kinetic equations to model particles within a gas bouncing around and creating a plasma. These are usually within a gap, and this gap can have certain parameters set upon it. The main task of my internship was to create a simple Python script that could help process 1D simulations faster, more efficiently, and create them specified by a user. The main task of my internship was to create a simple Python script that could help process 1D simulations faster and more accurately. And the second task of my internship was to run a series of tests on what type of voltage ranges could help create a stable plasma. Firstly, in creating the Python script, I had a few issues running Linux and SomaFoam. But later, after learning the basics of both of these, I was able to create a simple graph as you see below. Then, running the series of voltage ranges, although simple, took a long time. Each simulation took about 5 hours, as it had to have high accuracy and also had a longer runtime to investigate if a stable plasma was created. Overall, I had no stable plasmas created within the voltage range given to me by the professor. However, I believe this was a great learning experience on how to conduct research. On the side, I'd also conducted some research on if I was able to run some simulations faster by using the GPU. This, however, turned out to be inadequate, and I did not have enough time to test this during the summer internship. But I believe in the future it could be a potential avenue for furthering the software. Overall, this project was very interesting, especially in learning on how semiconductors were created using these types of plasmas. The next steps for this research would be to create a variety of scripts that can help analyze more complex scenarios as during the internship we only touched on a few voltage ranges and gap distances, and how they would affect the plasma in a one dimension. I also think that software-wise, the code could be improved by giving a UI interface and also GUI for a user to simplify and also can help with more research. I learned a lot from this experience, and I am thankful for Ayyaswamy and for CITRIS for giving me the chance to conduct this type of research. Thank you very much.
Hi, my name is Ivy Nguyen, and I'm a fourth year majoring in material science and engineering.
Hi, I'm Brianna Portilla, and I am a fourth year majoring in electrical engineering.
This summer, we interned at the Center for Nano Micromanufacturing at UC Davis, where we refined lithography baseline recipes. The production of smaller semiconductors allows more transistors to be placed on a single chip. Not only will this enhance the performance in electronics, it will also help increase efficiency in renewable energy, such as its prevalent use in solar panels. Chip manufacturing begins with the lithography process as shown in this image, which we aim to make slightly faster and more efficient for lab users. The lithography process, a printing process, contains a baseline recipe for various photoresist where the baking temperature, UV exposure dose, and development time are set to achieve an accurate pattern on the wafer. However, the results for accuracy can only be tested after the development. If an error did occur, such as a defective pattern print, we would have to restart the whole process. Therefore, to minimize the trial error, we tested and analyzed the parameters in baseline recipes to improve the accuracy.
Next, I will talk about the technical contributions we made throughout our internship. First, we created clear instructional videos regarding lab safety and chemical handling for use on the company website. We were also responsible for cleaning equipment parts through a process called bead blasting, as shown in these pictures. We aided in etching patterns into wafers through plasma etching. And we were also primarily trained in process monitoring, which is where we work to improve lithography processes. One challenge we would come across in recipe improvement is overexposed photoresist. This can occur for a variety of reasons, such as equipment dysfunction, exposing the wafer to too much UV light, or not enough time in the chemical development stage. The following pictures show a good example of photoresist patterning, as well as the case of overexposed photoresist. This can be judged by the clarity of the exposed pattern. We aim to change recipe parameters as needed to achieve clear patterns as demonstrated in the first pictures. This required a lot of trial and error. Throughout our learning, we learned about the importance of communication not only with each other, but with the engineering managers involved. With processes as delicate as these, our understanding of them had to be very clear. Also, with micro-scale details, we had to be able to pay extremely close attention to even the smallest of details. Because we will be continuing our work at CNM2 throughout the school year, we plan to continue testing and improving more baseline recipes to enhance the lab's catalog of recipes available to users. Some next steps for future students can involve exploring how our new recipes will affect etching efficiency and accuracy. Throughout our internship, I've been able to apply knowledge from various classes such as chemistry and device physics. We both have learned how connections between academics and career will be extremely important in the future. Our internship also involved a lot of communication and professionalism, as well as the ability to adapt to a workplace environment. We've been able to develop important workplace connections that can be beneficial to us in the future. Lastly, we would like to thank the managers and engineers who served as our mentors at CNM2 for graciously sharing their knowledge and support. We would also like to thank CITRIS for this great opportunity. Thank you.
Hi there, my name is Ryan. I'm a second year electrical engineering student at Davis.
And I'm Brian. I'm a fourth year computer engineering student at Davis. And this summer we had the opportunity to work at the AMCaT Lab in UC Davis.
So we primarily focused on three main projects: a publication scraper, automated grain analysis, and stereographic conversion.
And the main issue the lab wanted us to work on was automating tedious and lengthy tasks that would normally require a person to manually work on. More specifically, our project motivations were to determine statistics about machine and lab utilization.
For our other projects, we want to be able to automate the measurements of grain size and other techniques using many images. The third motivation was able to make a way to inspect the surface topography without having to destroy the material.
So, in order to determine the usage of the facilities, we had to look at various publications to determine if AMCaT facilities were used. The main challenges was the publication scraper, were being able to access the full text of different publications and getting a comprehensive search of all publications given a principal investigator. Another major focus of the project was being able to make it user-friendly from the organization of the files to the GUI that was made.
For the automated grain analysis, our goal was to be able to use machine learning to determine the individual grains and various attributes from size to the boundaries. Our focus was on determining what was a viable implementation for the machine learning. We also had to determine ways to validate that our results were correct. For the stereographic conversion, our focus was on how to use the SEM to get the best images in order to do photogrammetry and reconstruct the 3D object by using multiple images at different angles. After that, we determined possible programs that could be used and other alternatives, which balanced the ease of use while giving accurate results.
So moving forward, for the publication scraper, we want to have a more reliable way to access publications without using web scrapers, since they have various quirks to them. We also strive to continuously make improvements to the UI so that it can be more easily used. Lastly, we want to implement machine learning through natural language processing to determine the relevance of the publications.
For the automated grain analysis, the next logical step is to collect and add more data. We also want to do more extensive testing with other models to determine which is more accurate using methodologies that we discussed previously. We also want to make sure that the model can work for other grain materials. For the stereographic conversion, our main goal is to remove most of the user interaction and make it a much simpler process to process through. In closing, we would like to give our appreciation and thanks to the main staff like Dr. Andrew Sheritz for his guidance and opportunity to explore such great things. Thank you very much.
Hello, my name is Renata Lopez. I am a third-year computer science student at UC Santa Cruz, and the name of my organization is Vertical Architecture Memory and Algorithm Group at UC Santa Cruz. The problem that was aimed to solve during my internship was lack of equity access to real-world graph data. When researching graphs, real data is hard to come by due to it being owned by companies. For research purposes, it is more convenient to create synthetic graphs to test different graphing algorithms. My organization utilizes the GAP benchmark suite, which is intended to help graph processing research by standard evaluations. Within this program, the GAP benchmark uses graph generator ARMA to synthetically generate graphs that are later used for testing different graphing algorithms. This generator, however, has some limitations given it generates random graphs. However, most real data graphs are not entirely random and typically follow a community structure like the picture shown in the presentation. With that being said, my project consisted in implementing a synthetic graph generator with a community-like structure called BTER, which stands for Block 2 Level Erdos Renyi. Some of the challenges that I faced were trying to understand the research paper and the algorithm, given that there were a lot of terms that I wasn't familiar with. And then the next thing was trying to understand the complex pseudocode, because there were a lot of parameters and a lot of values given how this program is set up. I had to wrap my head around all of these different values and concepts. And the next challenge was identifying the best way of implementing this within the C++ language, which is the programming language used by the GAP benchmark suite. And then the last challenge was coming up with tests to determine the efficiency of the actual algorithm. For next steps after working on this project, The first will be to implement the code within the GAPBS benchmark or somehow test it together and use it to test different graphing algorithms that are already in the GAPBS benchmark suite. The second would be to do more testing and research on community graph structures. And the third one would be revising and optimizing code for better performance. Thank you so much for your time.